Hello everybody. Again I welcome you in the MOOC Massive Open Online course under NPTEL on plates and shell, and today I will deliver the lecture number 3 of the module 5. In module 5 I was discussing about the approximate method for the solution of plate problems. Actually there are many boundary conditions or loading conditions for which the closed form solution are not readily available, and even if closed form solutions are attempted, it becomes very tedious. So, therefore, the people lose interest in solving the closed form solution or finding the solution of the differential equation in a exact manner. So, therefore, there was a need for approximate method, and we have seen that based on the energy principle, we developed two very useful approximate method, which were known as Rayleigh-Ridge method and Galerkin method. Today, our discussion will be on the finite difference method in plate bending. Let us see the outlines of the lecture. First, I will find the derivatives related to the plate equation and boundary conditions in difference form. Okay. Then, I will convert the differential equation of the plate in finite difference equations. Finite difference equations for boundary conditions also have to be developed. Then, I will lastly illustrate an example of a plate, rectangular plate, whose deflections are found using the finite difference method. Okay. Now, let us see what is the finite difference method and why it is necessary. You have seen the differential equations of equilibrium in case of plate is a fourth order partial differential equation. This differential equation may contain the constant coefficients or it may contain variable coefficients if the thickness of the plate is not uniform. So, the complexity arises in case of such situation when we cannot find an analytical solution. But in our earlier problems or whatever problems we discussed using the classical approach, that is the Navier's method and Levy's method, and also for circular plate axisymmetrical formulation, where we assume that plate is of constant thickness, but sometimes the plate may vary in thickness. For example, you have a cantilever slab which is of varying thickness. So, in that case the modeling of plate with constant thickness will not be appropriate, and the solution of such problem using the classical approach is difficult and is obtained in very few cases. Okay. So, there is a need for finding the alternative method. Of course, the Rayleigh-Ridge and Galerkin method are two alternative methods, but there also you have seen that lengthy integrations were required to find out or to arrive at the deflected surface. Hence, a numerical technique is necessary. So, with the advance of computational facility in recent years, we can now use this type of method, that finite difference method, very easily to find the solution with reasonable accuracy. Okay. So, in this problem of plate, using the finite difference method, the differential equations are written in difference form at selected points in domain of the plate. So, what does it mean? Differential equation, for example, a simple example, if I say that dy by dx equal to say q, say any equation, first order equation, but this is a differential equation, I can solve it exactly. But if I want to express this in difference form, so I can write the dy as a difference of this y coordinate between 2 points 1 and say 2, and then divided by the distance between the 2 points 1 and 2. So, it is a simple example that this simple differential equation can be converted into difference form, that now it becomes a algebraic equation. But the accuracy loses, because the dx, that is the distance that we are taking between 2 points, if it is large, then the solution in this domain may not vary linearly. So, therefore, the solution of differential equation by difference form, if the interval is very large and assuming the linear variation, may not be appropriate. So, there is a source of error in case of difference form of equation, but this error can be controlled by suitable selection of the this grid size or mesh size. So, what is actually mesh? The whole domain is divided into rectangular or triangular or any other shape of this meshes, small elements, and the intersection or joints of the rectangular, triangular or other reference network that we call is the finite difference mesh. Okay. So, these points are located at the joints of rectangular or other reference network. The grid may be rectangular grid, or it may be triangular grid, or it may be any other shape of grid, but the joints that we name, that will be nodes. So, the differential equation has to be written in terms of the values available at the nodes. So, this is the principle. Now, in applying this method, the derivatives of the differential equations are replaced by difference equations, and thus the differential equation is now converted to algebraic equations. So, solutions of algebraic equations are only necessary in that case. So, the first task is to convert the differential equation into this difference form. Then we can apply this difference equation at the node covering the entire domain. So, we get a set of linear algebraic equations, and then solving this we can get the nodal values. For example, in case of plate, say rectangular plate, say A by B, if I divide this lengthwise direction, say 100 division, and widthwise direction I can also divide it 100 division or maybe other numbers also. So, in that case the intersection of this the lines, orthogonal lines, will give you the nodes, and at this node the value of the deflections are calculated from the solution of algebraic equation. How the algebraic equations are formed? Algebraic equations are formed after expressing the differential equation of the plate in difference form. So, the finite difference method is not only limited to this plate problem, it can be applied to any problem. Of course, here we will consider the static analysis of the plate, but in case of dynamic analysis also the finite difference method can be conveniently used. Now, necessity of the finite difference method is obvious, because suppose a plate which has two adjacent edges are fixed and other two adjacent edges are free. So, in that type of situation we do not get any classical solution readily available. So, therefore, we adopt a approximate method. Some approximate method that I told you, this Rayleigh or Galerkin method, can be applied, but again in that case the choosing the shape function can be chosen like a beam eigenfunction that I have discussed, but that requires a very rigorous integration, and then we can get this result. So, naturally the charm of solving the problem is lost by lengthy calculations or lengthy integrations. So, therefore, people try to adopt some numerical techniques and one of the popular numerical techniques is finite difference method. Other numerical techniques are also there. The finite element method is also a numerical technique. It can be used in plate problem, but finite element method is not included in the syllabus. Okay. With high speed computational facility, this method can be more attractive, because even say if I get 1000 equations, linear equations, simultaneous linear equation involving say nodal displacement at 1000 points in the grid points of the finite element meshes in a plate. So, there will be very less time consumed, because in computer, even in if you use the MATLAB, the linear solution simultaneous solution of the linear simultaneous equation is very easy. So, you can solve such type of problem with the high speed computers available in nowadays. Okay. Now, let us discuss the finite difference form of derivatives. Okay. The first and foremost thing in the finite difference method is to convert the derivatives involved in the differential equation of any physical problem to a difference form. Difference form is the difference between the nodal values, and how it can be formed for first derivative, second derivative, third derivative, because you require up to 4th derivative in case of plate equation. So, first let us discuss the finite difference form for the derivatives. Okay. Here we take a rectangular grids, and we divide the plate into with the grid, and we have selected the equal mesh size in both direction, x direction and y direction, but it is not mandatory. One can choose unequal mesh size also. Okay. Now, here you can see that deflected surface, if you see along the x axis or a section along the x direction, you will see this is the deflected surface. Similarly, if you see the deflected surface along the y direction, you will see this is the deflected surface. Okay. Now, at the nodal point, suppose this is the deflected surface drawn along this line, where the nodes are numbered 0, 1, 2, 3, 4, 5 in the positive direction of x axis, and -1, -2, -3 etcetera in the negative direction of the x axis. Similarly, if I take the downward direction as the positive direction of the y axis, then nodes are numbered as 1, 2, 3 etcetera along the positive direction of the y axis, and in the negative direction of the y axis is 0, -1, -2, -3. Our positive direction of y axis is downward. So, therefore, the negative values the negative numbering is given in the upward direction. Okay. So, you can see the deflection along this line at different nodes are, say here is node is W naught, then W 1, W 2, W 3, W 4, W 5. In the negative direction you will get W minus 1, W minus 2, W minus 3. So, this minus 1, minus 2 subscript that are used here only indicates the nodes along the negative direction of the x axis. Similar thing is existing along the y axis. So, you are getting the deflected surface along the y axis, but you can see that node 0 is common to x and y axis. So, you are getting here W naught. Okay. Now, here also in numbers say 1, 2, 3 along the y axis, and here minus 1, minus 2, minus 3 along the negative direction of the y axis. So, you are getting a deflected shape. Okay. So, our aim is to evaluate the deflection at the different grid points, because the exact expression of the deflected surface, say W x y as a mathematical function is not known for certain cases for of boundary conditions and loading. So, therefore, we need to discretize the domain into several grid points and then we evaluate this displacement in the at the grid points using this numerical technique, which is finite difference method. And then from the displacement values we can find the other stress resultant, like say bending moment in x direction, bending moment in y direction, twisting moment, then shear force, S shear, etc. Of course, when we consider the finite difference form of the derivatives, we have to also form the boundary condition, because boundary conditions also involves the derivatives of the function. For example, this bending moment. Bending moment is related to second derivative. Similarly, shear force is related to third derivative. So, we require the derivative also to be converted in the finite difference form. Okay. So, this is the finite difference grid point that I discussed, and plate is divided. Here of course, for illustration purpose I have taken the equal mesh size, that is the size of the mesh is h in x direction as well as it is h in the y direction. Okay. Now, let us find first the slope. Slope is nothing but the first derivative of the function. So, now at node O, or that is the 0 node, here we want to find the slope. So, this is found say in the forward direction, we have say the quantities are 1, 2, 3 etcetera from 0, and in the negative direction the quantities are minus w minus 1, w minus 2, w minus 3. So, we have taken the dw by dx at node O is nothing but the average slope at O towards its left and right side. Okay. Now, let us calculate what is the slope if we consider the displacement value on the right hand side, and what is the slope if we consider the displacement value on the left hand side. Okay. So, this is the displacement value on the right hand side, that is w 1 and w naught. So, difference of w 1 and w naught divided by the distance will give the slope of the line from this line that you are seeing 0 to 1. Similarly, on the left hand side, that is the backward difference, this is the forward difference, this is the backward difference. So, in the backward side, that is on the negative side, the slope will be say w minus 1, that is w naught minus w minus 1. So, this is divided by h. So, these two quantities are added and divided by 2 to take the average slope. So, after doing this algebra, that is summing these two slopes and divided by 2, we get ultimately the slope at O in the nodes. If the deflections at the nodal point 1 and minus 1 is known, then it can be calculated as w 1 minus w minus 1 divided by 2 h. So, this is the finite difference form of the slope. Okay. First derivative. Okay. Now, let us discuss this second derivative, because before discussing the second derivative, we write the finite difference form of each of the derivatives in this form, because this will be easy to remember. You see, the double circle here represents the node. So, at the node coefficient is 0. So, here you can see in the earlier case the final result is here dw by dx at O equal to 1 by 2 h into w 1 minus w minus 1. So, there is no value of the w at 0 appearing in this equation. So, therefore, if I write with 3 quantities, that means coefficient of w naught is 0, there is the center point. So, I can remember that this point is the node. So, I will place this stencil, this is called stencil, if I place this at O, then I will get the right hand side value, deflection value has to be multiplied by 1 and left hand side deflection value has to be multiplied by -1. So, these are summed up and divided by 2h, then I will got the slope. Okay. So, double circle refers to the point under consideration, that is we call it node point. Okay. Similarly, the second derivative, that is the curvature at point O, can be calculated, because I have used the word approximated, because the finite difference equations are approximate equation. So, these values are approximate. Okay. So, similarly, second derivatives are calculated. Second derivative is nothing but the rate of change of slope between center of this site, say O minus 1, this center, and other center is considered O to 1. So, between those two points the curvature is calculated. Okay. So, curvature is calculated say del square W by del x square is nothing but the rate of change of slope. Okay. So, slope is this and rate of change, that is del by del x into del W by del x. Okay. Now, here we know that dx is here 1 by h. So, directly we substituted 1 by h, but change of slope dw by dx is the rate of change of displacement, that is the slope between the 2 points minus h by 2 to between minus h by 2 to plus h by 2. Okay. So, we get this 1 by 2 h. So, here instead of this 2 h, because minus h by 2 to plus h by 2 distance is h. So, we have kept here h and the value is W 1 minus W 0 and minus, because change we are evaluating the change. So, W naught minus W minus 1 divided by h. So, after simplification we get W minus 1 minus 2 W naught plus W 1 divided by h square. So, this equation has some implications. Okay. That means, it is the second derivative, and this equation when you use, you have to place the stencil I will show in the next slide, that is the stencil for your this slope, but for derivative also stencil can be constructed. So, in that case if I place the node here, this stencil here centering at O, the coefficient here is minus 2 and then other two values here will be 1 and 1. So, minus 2 is only the coefficient of central point, that is the node, and towards right and towards left the coefficient is 1. Okay. So, in that fashion we can now express this. Okay. Now, you can see this is the stencil for curvature. So, center point is coefficient of deflection or this at the node concern node, that is the node 0 is minus 2 and towards right it is 1 and towards left it is minus 1. Okay. Towards left also plus 1. So, these are the coefficients. Okay. So, that indicates that the curvature quantity that we have taken is between the change we have taken 1 2 and minus 1 and divided by 2 h. Okay. So, this h actually the distance between 2 points that we have considered is from minus h by 2 plus h by 2. So, generally h comes. So, therefore, ultimately the equation becomes in terms of h. Okay. Let us now calculate the third derivative. In the third derivative, once this is known, so we can make use of this equation and then we take again the rate of change. Okay. So, del square W by del x square now can be written, because at the 2 points if you consider covering say 0, 1 and 2. okay, 0, 1 and 2 in the forward direction. If I write this quantity in the forward direction and other quantity in the backward direction. Okay. So, in that case if we write this second derivative, we can write w naught minus w 1 plus w 2, and here we can write w minus 1 plus w naught and plus w minus 2. So, all this quantity will be divided by a square. So, after simplification you get the difference form of the third derivative as 1 by 2 h cube bracket minus w minus 2 plus 2 w minus 1 minus 2 w 1 plus w 2. Now, here you can see in the third derivative equation, this quantity w naught get cancelled. Okay. So, there is no w naught appearing here, that means coefficient of w naught will be 0. So, if I write in the stencil form, you see this is the node, we are considering the node at O. So, this is the coefficient at the node which is 0. Towards the right side the coefficient is minus 2 minus 2, okay. And then on the further side it is plus 1. So, here it is plus 1 w 2. So, similarly it is also given in the towards the left hand side, it is plus 2 and it is minus 2. Now, one thing you can note here, it is very interesting to note that the odd derivatives that are antisymmetric. Okay. If I consider this is the line of symmetry, okay, line of symmetry. So, on the positive side you are getting minus 2 1 coefficient, on the negative side you are getting 2 minus 1. So, this is completely antisymmetric. So, our calculations are correct. Okay. The above equation may be derived conveniently by following pattern operation also. Okay. So, what is pattern operation? That means we know del square w del x square, and also we know this operator because we have calculated the slope. So, we write this operator 1 by 2 h minus 1 0 plus 1, this is the operator that I have written. Then second is this del square w del x square. So, this operator is this 1 by h square 1 minus 2 1. Okay. So, pattern operation means here you just expand it. So, I multiply it say this with minus 1. So, minus 1 minus 2 into minus 1 plus 2, then minus 1 into 1 is minus 1. Okay. Then I am multiplying this all the terms by the second term 0. So, that is 0 0 0 and it is starting from the second column. Then this third term here I am multiplying it 1, then minus 2, then 1. Okay. Then if you add all this column wise, then we will get here 2 h cube is the factor bracket, this is minus 1, this is 2 and this is 0, plus 1 minus 1 will be 0, then again it is minus 2 and 1. So, this is same as this, and you can see here that antisymmetric pattern is observed. Okay. Antisymmetric pattern is obvious here, and it is true because it is a third derivative, odd number of derivatives. So, antisymmetry should be reflected in the expression. Okay. Next we consider the last derivative, that is because our plate is equation is of fourth order. So, we must go up to the fourth order derivative. So, if I calculate or if I want to express the fourth order derivative in finite difference form, I can write that del square dx square into del square w del x square. Okay. So, again I use the pattern operation. Okay. So, pattern operation is used here, and then this is actually this operator for curvature I have written here. Then here again this the curvature between the points that I have written. Here the w is associated, but here it is only operator del square del x square. So, you can distinguish. So, first thing is the operator that I have written del square by del x square, and this is del square w by del x square, in which the subscript w is associated. Okay. Now, again you do the same operation that I have done in the earlier cases, multiply each term. So, 1, then minus 2, then 1, then minus 2, plus 4, minus 2, then 1, minus 2, 1. Okay. So, fourth derivative is now obtained. So, fourth derivative will be 1 by h to the power 4 bracket 1, if you add this 0, then add it 6 and again add minus 4 and again add 1. So, this quantity will be 1 by h to the power 4 bracket 1 minus 2 addition, okay, addition not subtraction. So, addition minus 2 and minus 2 minus 4 and 1 plus 4 plus 1, that is 6, then this term is minus 2 is minus 4 and lastly is 1. Now, here you can see that because it is a even derivative, so the symmetry is obeyed, symmetry pattern is obeyed. So, how it can be obeyed? Say here the center value is 6, 1 plus 4 plus 2, 6. On the left hand side you are getting minus 4 and 1, right hand side also you are getting minus 4 and 1. So, in the stencil form I can write it 6 minus 4 1 minus 4 1. So, it is completely symmetric, all right. So, we have obtained the finite difference form of the derivatives with respect to x. So, if I want to write or express the derivative with respect to y, similar this procedure can be adopted without any difficulty, and here in case of writing the derivative in stencil form, we just rotate it 90 degree. So, we get the difference form of the derivative in the stencil pattern with respect to y when we differentiate it, first derivative, second derivative, third derivative and up to fourth derivative. We just obtain the previous results by rotating it 90 degree. Okay. So, first result that we got, say slope, let us see, slope we got, this is the horizontal line, that means it indicates along the x axis. So, 1 0 1. So, if I rotate this 90 degree, I will get del w by del y. So, here this pattern is noted, del w by del y is 0 is the nodal value, and towards the negative side it is minus 1, towards the positive side 1. Similarly, the second derivative, the value was 1 by h square and 1 minus 2 1. So, it is written after rotating it 90 degree. Then your third derivative is written accordingly after rotating the stencil of the third derivative. Third derivative stencil is this, third derivative stencil is this, just we rotate this 90 degree and we got this third derivative difference form. Similarly, fourth derivative difference form is written 1 by h to the power 4, and then the symmetric pattern is also observed along the y direction. Okay. Now, the finite difference form for the plate equation have to be obtained. Okay. So, we know difference quantities, that del square w del x square, del square w del y square, etcetera. And then if I express w with the Laplacian operator del square w, I can write del square w by del x square plus del square w by del y square. So, now write in the stencil form, this quantity means del square I first written, del square w by x square I have written here, plus del square w by del y square I have written, because this is derivative with respect to y and this is derivative with respect to x. So, same thing is there, but one is rotated by 90 degree upward. Okay. And here you can see that the h is the grid size that is taken equal in x and y direction. If the grid size is not taken equal in x and y direction, then this h, suppose this is h 1, then it will be h 2. So, then you can express the equation in terms of h 1 by h 2 ratio. Okay. That is also possible. There is no difficulty if one take unequal meshes, rectangular meshes. Okay. So, after adding, okay, if these two are added, very easily you can see that del square w is nothing but 1 by h square 1, this term will be 1, and then minus 2 it is minus 4, then it is 1, then in the vertical side you are getting 1 and 1, of course, this term will be 0, there will be no coefficient appearing at the corners. So, this is the del square w by del x square plus del square w by del y square equation in finite difference form. There is the Laplacian equation, that very important equation. Now, here you can see if I remove w, then this term represents the operator del square. Okay. Now, it is possible for us to find out the finite difference form of the plate equation. How can we form? Because we know the Laplacian operator. So, finite difference form of the plate equation is found writing this del 4 w equal to del 4 w into del square w into del square w. Okay. So, this operation can be written, that is, if in expanded form the plate equation is like that, del to the power 4 into w by del x to the power 4 plus 2 del to the power 4 w del x square del y square plus del to the power 4 w del y to the power 4 equal to q by d, where q is the distributed load. Okay. Now, d is the flexural rigidity of the plate, it has no connection with the grid size. Okay. It is a constant quantity, depends on the material properties, and q is the distributed load. Of course, when we convert the finite difference form in the distributed loading, at each node the load has to be expressed. Okay. So, left hand side of this equation now becomes it is how it is found? It is found by this operational procedure that we have adopted earlier for this case, say like that. So, here also if you adopt this procedure, then you will find out the left hand side of the plate equation, that is del 4 w. Actually, del 4 w is nothing but 1 by h to the power 4, and in the central line along the horizontal direction you are getting 5 terms. So, for example, here it is centering at node 0. So, w 0, then w 1 and w 2, here w minus 1, w minus 2. In the y direction, whatever value you take in the y direction, it can be represented. Okay. Now, these are the coefficients of the nodal displacement. When you place the stencil at the nodes, the nodal displacement say at the node, say center node is say 0. So, it will be expressed, this quantity can be understood as 20 w 0. This quantity may be understood as minus 8 w 1. This quantity may be understood as 1 into w 2, like that any other quantities can also be interpreted. Okay. So, the plate equation in the stencil form, that is now our important tool to be applied in a problem using the finite difference form. So, this stencil now you are seeing here the 20 minus 8 and 1 1. So, this when you place the stencil at a node, then it covers centrally these 5 points, okay, horizontally, and vertically also 5 points, then other 3 points. Okay. Then you can see this stencil is symmetric, because the fourth order equation we are writing. So, it is a symmetric matrix, and q h to the power 4 by d, where q is the load at the nodal point. Okay. nodal point load has to be taken. Okay. H is the mesh size. If the mesh size is different, then of course, this equation will be slightly modified in terms of say ratio of mesh size in x to the y directions. Okay. So, now expression for stress resultant, let us see the expression for stress resultant. First, let us see what is mx bending moment. Okay. Bending moment expression, you can see that it is second derivative of w d square w dx square plus mu into del square w by del y square. Okay. Here you can see first what I have written this del square w by del x square. So, this quantity is taken from the earlier expression that I have derived plus mu into del square w by del y square. Del square w by del y square same quantity, but it is written in the vertical direction, because the derivative is taken with respect to y. Okay. And the Poisson ratio mu is associated. So, that is must. Okay. Now, after adding, okay, because this is plus sign is there. So, after adding, you are getting centrally this minus 2 into mu. Okay. And then this mu has to be multiplied with all the coefficients here with the difference form of del square w del y square. So, therefore, here vertically this mu up and down mu plus mu appears. Okay. Then on the other side, that is 1 is there. So, 1 and 1 is there, because there is no coefficient or no other parameter involved with 1. Okay. So, this is the stencil form of the bending moment in x direction. Bending moment in y direction can be written just by rotating it vertically. Okay. So, here in that case, for derivative with respect to y, second derivative, this mu and mu comes here in the horizontal line, and this is del square w del x square, it is coming in the vertical line. Okay. mxy can also be written minus d 1 minus nu del square w del x del y. Now, here del w del y we expressed earlier in the difference form. Now, we are operating with del by del x. So, it can be written in this form, and you are getting here the mxy is very interesting expression minus d 1 minus mu divided by 4 a square, and then 1 0 minus 1 0 0 0, the central value along the row is 0 and along the column is also 0. Only you are getting the coefficient plus 1 or minus 1 at the corners. So, 1 minus 1 and minus 1 and 1. So, this is the value of mxy. Okay. So, it may be easily seen that the shear force is nothing but minus d del by del x del square w. Okay. The del square, that is if I expand it, it will be del square w by del x square plus del square w by del y square. So, after operating with this, because del square w we already found out, del square w is this, del square w is this quantity. Okay. This quantity. So, once you find this del square w, then after taking this rate of change of del square w, we now get the shearing force q x as minus d divided by 2 h cube bracket minus 1 0 1, then horizontal line you are getting minus 1 4 0 minus 4 1 minus 1 0 1. One thing also you can note here, that shearing force, because it involves the odd derivatives. So, you are getting antisymmetric term. So, here it is minus 4, here it is plus 4, here it is plus 1, here it is minus 1. Okay. So, you are getting antisymmetric term. Okay. So, S shear force, that is we need to apply this condition specially at the edges. For such edges where the boundary condition is that the force boundary condition has to be imposed. For example, free edge. Free edge we know that the shearing force is 0, then twisting moment is 0 as well as bending moment is 0. Okay. So, 3 conditions are necessary and 3 conditions of free edges are given by Poisson that I told in my earlier lectures. Now, the 3 conditions are combined by Kirchhoff mathematically to give 2 conditions. So, one condition is bending moment and another condition is S shear. So, in the S shear expression you will find that 2 quantities are involved, that is q x and m x y. So, twisting moment and shearing forces are combined to form the S shear force expression. So, S shear force expression is this, tensile is like that, that is in the horizontal line along this center you are getting center value is 0, towards the right hand side you are getting minus 4.5 plus 0.5 mu, mu is the Poisson ratio and then you are getting 1, then towards the left hand side you are getting 4.5 minus 4.5 then minus 1. Here also you are getting this antisymmetric pattern, very clearly it is observed. Then in the vertical side along these edges, because it is the shear force along the edge where x is specified. So, along this direction at the central line you are getting 0 values, 0 coefficient. Then other columns are written as towards right it is 1 minus mu divided by 4, 1 minus 4.5 plus 0.5 mu, then 1 minus mu divided by 4. In the left hand column you are getting minus 1 plus mu divided by 4 minus 1, then minus 1 plus mu divided by 4. So, antisymmetric pattern is noted. Okay. Now, by rotating q x and v x pattern by 90 degree. Now, this thing we have obtained by pattern operation, okay, but if you rotate it by 90 degree you will get this q y and v y. So, it is easily obtained this rotating this tensile by 90 degree. Okay. Let us come to the boundary conditions. Okay. Now, plate in general may have various common boundary conditions or very non-classical boundary condition, what we call. Common boundary conditions are classical boundary condition, that is either pinned, that is simply supported, or clamped or free. These are the classical boundary condition. Non-classical boundary condition may be spring supported, may be supported on the elastic beam, may be supported by rotational springs or in any other manner. So, that type of boundary conditions can also be expressed knowing the edge values. Now, here let us discuss the only classical boundary conditions, that is simply supported, fixed and free edges. First we will give the expression for simply supported and fixed edges, then we will go for this edge, this free edge. Okay. Let us consider the simply supported edge. Okay. In the simply supported edge, this edge is simply supported, this vertical edge. So, nodes are in the edge, the nodes falling are 0 to 4. Okay. 0 to 4 are the nodes that is falling on the supported edge. So, naturally the deflection values at 2, 0 and 4 are 0. Okay. Now, we have to place the stencil for bending moment at the node 0 here at the edge. So, if I place the stencil here, that means this center value is now placed at 0. Okay. Center value is placed at 0, very carefully note it. So, you get one value outside the plate, okay, outside the plate. So, how to consider this? Now, this is given by taking the imaginary nodes towards the left or towards the right, vertically or horizontally, and imaginary grids I have taken whose size is same as this size. Okay. Now, imposing this condition, if I place these grids one point is on the imaginary point grid point and other is on the real grid point. So, this point is called the this is the image point and this is the imaginary point. Okay. Now, if I express the deflection of a simply supported plate, because this point deflection is meaningless, because this is imaginary. So, we have to express the deflection of the point 1, that is on the imaginary grid, to the deflection corresponding deflection of the image point. The image point is 0.3. So, now if I see the condition, okay, here if you see the condition, simply supported case, the deflection will be like that, okay, because rotation is permitted. So, there you will get slope. Now, since the grid size are equal, and from this condition you can see, if because it is falling on this one, that is the imaginary grid. So, W 1 plus W 3, because this is also falling on this real point, that is image point, and coefficient is 1. So, W 1 plus W 3 is 0, and these points are falling on the edges. So, naturally this value will be 0, this deflection will be 0 here, 2, 0 and 4. So, now we can express this boundary condition as W 1 plus W 3 equal to 0. So, W 1 equal to minus W 3, that is the deflection of imaginary point is equal to the negative of the deflection of the image point. Image point is 3 here. Okay. Now, let us go to the fixed edge. Okay. Fixed edge condition is depicted by del W by del x equal to 0, and the deflection is also 0. Okay. Now, when this stencil is placed here, okay, then it is falling on the 0 is the center. So, other values are at the imaginary point 1 and 1 value at the image point. The value of the deflection at 2, 0 and 4 are 0, okay, because this is falling on the fixed edge. All right. So, now if I express this, you can see here this coefficient is minus 1. So, minus W 1 plus W 3 equal to 0. So, therefore, we are getting W 1 equal to W 3. So, in this case, the displacement of imaginary point is equal to the displacement of image point. Okay. So, at the free edge, imposing this condition m x equal to 0, V x equal to 0, where V x is the Kirchhoff's edge shear, one can write the boundary condition. Okay. Now, let us illustrate a problem of rectangular plate that has to be solved by finite difference method and fixed along the boundaries. Okay. So, for simplicity, I have taken the equal grid size and I have taken a square plate for illustration purpose, but it is not mandatory. You can take any unequal grid size also. Okay. So, we have to find the deflection at the center of the plate and moment at the center, because moment at the center will be equal in both direction because of symmetry, and the plate is subjected to UDL. So, at each node the value is say q. Now, since the slope is 0, we get W minus 1 equal to W 1. So, that relation has to be valid from viewpoint of boundary condition. Okay. Now, first we plate number the nodes. Okay. Now, because of symmetry, we can see here, if this is the center point, that is numbered as 1, you can see these are the points of symmetry 2, 2, 2 and 2. So, here the W values are equal. So, these are also symmetry point 3, 3 and here 3 and 3. Other nodal points are falling on the edges in which deflections are 0. So, I have not numbered. Okay. Naturally, it will be substituted as 0 value. Okay. Now, let us place the stencil for the plate equation. This is the stencil for the plate equation that I have shown earlier, and this is placed here at the node 1. Now, you can see after placing the stencil at the node 1, the 20 is here and minus 8 1. Okay. This 1 is falling on the edges. So, naturally, there will be 0 value. Then again this is minus 8 and 1, this is falling on the edges, this is minus 8 1, this is falling on the edges, this is also falling on the edges, and these are the points here coefficient 2. So, naturally 20 W 1 okay, minus because of symmetry now these values are equal, deflections are equal. So, this we can write this 4 into 2 W 3 okay, these are the 0.3 okay. Then this minus coefficient is minus 8. So, 1 minus 8, 1 minus 8, 1 minus 8, 1 minus 8 where the deflections are equal. So, we write minus 4 into 8 W 2. So, this is the equation and right hand side is q naught h to the power 4 divided by d. So, after simplification we get this. Okay. Now, next place the stencil at the node 2. Okay. After placing the stencil at node 2, you can see that this minus 8 here and 1 is falling on the edge. Okay. So, naturally the deflection this will go to 0 because there will be no deflection at the edges. Similarly, here and here you are seeing minus 8 and here 1. Okay. But now, you can see minus 8 is falling here, but another point is falling on the imaginary point. So, imaginary point if you see at a same distance here. So, imaginary point deflection will be equal to deflection of point node 2 because of the condition that we have derived. So, therefore, one imaginary point deflection I have written with a red color that you can understand it, and other values are easily written this 20 W 2, then minus 8 W 3, minus 8 W 3, minus 8 W 1, plus 2 W 2, plus 2 W 2. Okay. So, another 2 W 2 W 2 will come here and then imaginary point W 2. Okay. So, this is q naught h to the power 4 divided by 2 because this load is uniformly distributed. So, after simplification we get this value. Okay. Next, the plate equation is to be written at nodal point 3. Any of the nodal point you can choose because these are symmetrical points. So, after placing the stencil at 3, we can now write okay, the equation, nodal equation. So, nodal equation if you write, you can see if I place the 20 here, one node imaginary node you are getting in the vertical direction and one imaginary node you are getting in the horizontal direction. So, therefore, two imaginary nodes because the image point will be 3, one imaginary node goes here whose image is 3, another imaginary node goes here whose image is also 3. So, W 3 are written which are red color to understand that these are the image points and corresponding imaginary point deflections are related to the image point deflection. Image points are node 3 and other values can be usually written 20 W 3, okay, 20 W 3 minus 8 W 2 minus 8 W 2 plus 2 W 1 plus W 3 plus W 3, only these reflect the image point corresponding to imaginary point in the vertical as well as horizontal direction. Okay. So, we get 3 equations and our unknowns are 3 because of symmetry we get this advantage, and now solving these equations by any method, this can be expressed in matrix form like that, the 20 minus 32 8 minus 8 26 minus 16 2 minus 16 24. This is a 3 by 3 matrix, coefficient matrix, and the unknown vectors are W 1, W 2, W 3 unknown variables, and this is right hand side is written. After solving we get W 1, W 2, W 3 as this. Okay. Now, let us calculate the moment because another question was that second part was to compute the moment at the center. Because of symmetry of the support and symmetry of the loading, we found that the mx equal to my at the center. Okay. And mx into my at the center can be calculated. This is the stencil for mx or my, whatever you call. Now, this is to be placed at the node 1, 1 is the central node. So, if I place node 1 stencil here 1 at 1, then what we get? We get this say minus d by a square, this is okay. Then we get this central node minus 2 mu, this is the coefficient into W 1. Okay. Then on the right hand side we are getting this W 2 is there. On the left hand side again W 2 is there, and on the vertical direction we are getting mu into W 2 and mu into W 2. Okay. So, since W 1 and W 2 are known, so substituting this and simplifying, we get the expression for bending moment like that. At the center it is equal to 0.02465 q naught h square, h is the grid size. Okay. Now, if you see that of course, if this is the written in terms of h, it can be converted into original size of the plate, because h we have taken as a by 4. So, it is written like that. And now, let us give a question to you. If you understand this, you will be able to answer. What will be the twisting moment at the node 2? Because now we found the deflection value at the nodal points, we can now calculate any stress resultant. So, let us proceed to calculate the twisting moment at 3. Twisting moment at 3 is calculated. This is the stencil for twisting moment. It is placed here at 3 and node 3, and you can see it covers this point, right hand side 1 point, left hand side 1 point horizontally, and also in the vertical side, that is 1 point this, another point this, and here again another point, this is other point, and these are other points. Okay. Now, you can see, because the nodes here, if I place this stencil, these are the edge nodes. So, naturally no deflection is there, and again this is these are the edge nodes, this and this edge nodes. So, there will be no deflection, even if there is a coefficient here 1 minus 1, there will be no deflection. Central node has no 0 coefficient, so no deflection. Vertically, if I see along the central line, so there is also 0 coefficient, so no deflection. Only you are getting here the meaningful coefficient, that is 1. So, this deflection is W 1. So, therefore, the mxy is written this coefficient into W 1. Now, substituting the value of W 1 that we have obtained earlier, we now write this is the value of W 1, and now this is minus d 1 minus 0.3 is the Poisson ratio 4 h by 4 h square. So, it is kept in terms of grid size, but however, if you want to express this in terms of plate dimension, then h can be replaced by a by 4. Okay. So, this is the application of finite difference method in case of plate problem. Okay. We have taken an example of fixed plate, but other boundary condition can also be taken. So, let us summarize the lecture what I have delivered today. In this lecture, finite difference method applicable to plate bending has been discussed, because finite difference is a very vast topic. It can be applied to beam bending, buckling of column, vibration problem, but I have taken only the plate problem. So, discussion was carried out related to only plate bending. The finite difference form of first, second, third and fourth derivatives and also cross derivatives are obtained in terms of nodal deflections first, which are then used to convert differential equation of plate and boundary conditions to finite difference form. The method is illustrated with an example of rectangular plate which is clamped along all edges. Now, you have noted that because of difference form, there was no need of solving any differential equation. Ultimately, differential equation is converted in a algebraic equation, and this is very easily solved, because the conversion that took place yields a linear simultaneous differential equation. In variables are nodal deflections. So, depending on the number of node points you can take, that number of equations will increase, but nowadays with the help of this computational facility, there will be no difficulty to obtain to solve n number of simultaneous linear equations. Thank you very much.